Hello and hi everybody. So today we are from group 9 want to share about frequencies response of a circuit. So the first thing I'm Muhammad Ifan bin Jumain and three more members, group members which is Muhammad Naim bin Osman, Adil Uman bin Idris and Andrew Pohwemi. A bit preview, what we will share today is how to conduct, how to obtain, how to draw the bot plot graph through the transfer function given, and how to obtain the transfer function from the bot plot given. So let's go. Okay, so first of all, I want to make a big introduction for frequencies response of a circuit. It is the variation in the circuit behavior with change in signal frequency and may also be considered as the variation of the gain and phase with frequency. Uh, Next, we will go to the problem part.
The problem we are looking at is how to understand the frequency response of a circuit. This means looking at how the circuit respond to different frequency. We also need to learn how to draw a dot plot using a given transfer function. A dot plot shows how the circuit behave. Finally, we want to know how to find the transfer function from a given dot plot. These steps help us understand and design circuit better. The goals of this lesson are clear and straightforward. First, we want to understand the frequency response of a circuit, which help us see how circuits react to different frequencies. Next, we will learn how to draw a dot plot using a given transfer function. This is an important skill for analyzing systems in the frequency domain. Finally, we will learn how to work backward by converting a dot plot into its original transfer function.
Before we dive into pop plots or any juicy frequency response analysis, let's get crystal clear on what a transfer function even is. Trust me, this is the golden key to unlocking everything else. So, the transfer function denoted H omega is just a fancy name for the ratio of output to input in the frequency domain. In other words, H omega is equal to Y omega over X omega, where X omega is your input signal like voltage or currents, and Y omega is the output after it passed through a system or network. As shown here in the block diagram, we have got an input signal x omega. It enters a linear system. Our mystery box marked h omega. Out comes y omega. This relationship gives us insight into what the system does to different frequencies. And we are not just interested in the radio. We want to know how much the output changes magnitude and by how much it lags or leads in times phase. That's why we write h omega in equal to h omega magnitude angle phi to include both amplitude scalings and phase shift. This concept is core to control system, filter, communication systems. It tells us how a system reacts to each frequency. Some frequencies pass through, other get squashed. So keep this in mind when we look at a Bob plot or calculate system respond. We are just analyzing how H omega behave over a different frequency. Now let's use this power in the next line.
Alright, now we have bot plot. So what are bot plots? Bot plots are the semi-log plots of the magnitude in decibel and phase in degree of a transfer function versus frequency. Now that we know that, let's talk about how do we draw the line in the bot plot. First we have first we have k. So what is k? K is the gain of the bot plot. How do we draw it? Basically, we just need to draw one straight line at 20 log 10k. So find the value of k, insert it into the equation, 20 log 10k, and then we can get our line. Which point we need to we need to draw the line. The phase, same thing, the straight line, but at 0 degrees. 0 degrees. Then as well, we have j omega. J omega here is a 0 at origin. How we draw it? First, we need to draw one line. You can see the black line here. The black line start at 0 dB. Start at 0 magnitude in decibels, so 0 dB. And then we need to draw one line intersecting the first frequency, so 1. And then it will increase by 20 dB. So it will increase by 30 dB per decade. So the next decade, if you see, so next decade of 1 is 10. So it will increase by 20 dB there. So we need to draw one line intersecting that. The next one here is 1 over j omega n. This is our pole at origin. It's the same as 0 at origin, but instead of going up, it goes down. So it's negative 20 dB. The slope goes down. This one, the slope goes up. The omega for 0 equal, the slope goes up, while for pole, the slope goes down. Same thing as phase. We just need to draw one straight line for the both, but for 0 at origin, we have 90 n above, and for pole at origin, we have negative 90 n. Alright, the last one here, we have 1 plus j omega over z. This, what you call this one, this is a simple zero for a pop plot. So how we do it? First, we just need to find the value of z in the frequency section. So let's say z here down here is equal to 1. So we just draw for the we just take line starting from 0 dB. Just go straight into the value z, and then go up by 20 dB per decade to the next dB. So let's say z is equal to 1. At 10, it will increase by 20 dB per decade. You see, it just increased it. Same as the bottom one here, but it become 1 over 1 plus j omega over p. And it's basically the same as this, but instead of simple 0, this is simple pole. So it went down, the slope went down, but it followed the same rule. Just start from 0, go to the value of p, and then goes down. The slope goes down at negative 20 dB per decade. Same as the phase diagram. So a little bit of information we have here, say quadratic pole. Quadratic pole happens when, let's say, 1 plus j omega over z, we have a power of 2. So when 1 plus j omega over z, we have a power of 2, instead of increasing by 20 dB, it will increase by 40 dB. So it will go straight up to 40 at this decade. So let's say z equal to 1, at 10, it will increase by 40 dB. Same as the bottom one here, we have 1 over j omega, 1 plus 1 over 1 plus j omega over p, and here will be negative 2, power of negative 2, and then it will go down by negative 40 dB at the next decade. So that's how a little bit about how we draw the bot plot.
For the question B, transfer function given, we need to find a few important things. First, we must write the general form of the equation to create the dot plot. Then we will draw the magnitude dot plot on a semi-log graph. After that, we will draw the first dot plot on the same kind of graph. Finally, we will identify the zero and poles of the transfer function. And then the transfer function we are using is h omega equal j omega plus 10 over j omega multiply j omega plus phi square. To convert the transfer function into standard form, we start with the function h omega equal j omega plus 10 over j omega multiply j omega plus phi square. First, to simplify, we multiply both the numerator and denominator by helpful constant to facilitate factoring. Specifically, we multiply by 10 over 10 in the numerator and 5 over 5 square in the denominator. They give us h omega equal j omega plus 10 multiply 10 over 10 over j omega multiply j omega plus 5 square multiply 5 over 5 square. Next, we factor the terms to express them in the standard form. The numerator becomes 10, 1 plus j omega over 10, and the denominator becomes j omega 1 plus j omega over 5 square. Substitute this in, we get h omega equal 10 bracket 1 plus j omega over 10 over j omega multiply 1 plus j omega over 5 square and multiply 25. Now simplify the constant. We get h omega equal 10 multiply 1 plus j omega over 10 over 25 multiply j omega multiply 1 plus j omega over 5 square. Finally, reduce the constant to simplify the function into in standard form, and we get h omega uh, equal to multiply 1 plus j omega over 10 and over 5 multiply j omega multiply 1 plus j omega over 5 square. This is the transfer function expressed in standard form.
Okay, now we are going to draw the line on the dot plot. Lah. So now, based on our previous conversion, we get the final transfer function, which is 2 in bracket 1 plus j omega over 10 over 5 j omega 1 plus j omega 5 2. Now that we know that, let's go it one by one. So let's start with 2. You see 2 is outside of the bracket, right? And there's 5 down there. So we can basically just divide these two numbers and we can get 0.4. So when we get 0.4, we can then put the value, which is going that 0.4 will be our k value, and then we can put it into our log. So 20 log 10 0.4, we can get the value of negative 8 dB. So we can draw our straight line, which is the dB gain straight line, just at negative 8 dB. So just draw one straight line across it. Okay, you can see the blue line there. That is our gain dB line. Gain dB line. Now next to it, we have 1 plus j omega over 10. Now this is our simple 0. So how we draw that? First, we take a look at the frequency. The frequency here is 10. So first, we just draw one straight line, going to follow the red line here. So just draw one straight line until it reach the decade, the frequency here, which is 10. And then we need to go to the next decade, which is going to be uh, um, which is going to be 100. So when it's at the 100 dB, we need to increase it by 20 dB. We need to draw one slope at positive 20 dB. So just mark one point at 10, another one at 100, and then just one more at 10, then another one at 100, and then just draw one straight line across it. Now 5 down there is already been settled away. We have j omega. Now j omega here, because it beneath in the equation, this is our pole at origin. So first we need to draw one line at 0 dB. So look at the big line here. There's our 0 dB line. Next we need to draw a line that intersect with 1 dB, and the slope will be negative 20 dB. So the slope here will start at 1, it will intersect at 1, and then we'll go down by negative 20 dB. So yeah, you can see the slope here, the green line, just go down as low at negative 20 dB. The last one here, we have 1 plus j omega over 5 power of 2. Now this is because it's below, instead of becoming a 0, it will become our pole. So this is a quadratic pole. So the same as a simple pole, but you can see the orange line here. Just go until it stop at 5 frequency, our frequency equal to 5, and then it will then go straight down by negative 40 dB. So you can see the orange line there, it just goes straight down to negative 20 dB. Alright, now we know about that. Is the line, is the ball plot finished? Not yet. We need to draw one final line, one finalization line. So how do you draw that? First, we need to take note of the critical point, which is 0 0.1, 1, 5, 10, 50, and 100, and so on. You can continue, but there is our critical point for now. So how do you draw that? First, we need to figure out the value on each of every single critical point. So let's say we're starting at 0 0.1, correct? And here we have the value of 0, which is all we have negative 20 dB, sorry, positive 20 dB from our pole at origin. We have 0 dB for almost every single other thing, which is our simple 0 and our quadratic pole, and we have negative 8 dB at our gate. So we just add the two numbers. So negative 8 dB plus 20 dB by the value of 12. So we just mark a point at 12. Then we continue on. The next one is at 1. So at 1 dB, you can see the value here is 0 for both pole, and for both pole at origin, simple 0, and quadratic pole. But our value for gain here is still negative 8. So we just mark another one at 1 dB for negative 8. This one, another plot there, another point there. So now we have 5. So at frequency 5, how much has changed? You can see for the value of 0 dB for our quadratic pole and our simple 0 doesn't change because it's still 0, but the value for our pole at origin changes. We have the value of, I believe this is 14, negative 14. So negative 14 plus by negative 8, we have the value of negative 22. So we have the value there. Continue again. We have when the red is equal to 10. So equal to 10, how much changes? Just find the value, and then we just keep adding them together till we have our another point, so we can draw the line, connect them to draw a line. Then the last one at 50, same thing. We just find the value for each one, and then we just draw, you just plot it, and then just connect the line together to create this finalization line, the black line, the finalized line. So this is the true uh, this is true value of our transfer function. Show the changes in the transfer function. Yeah, that is all.
Here we have question G, and it's asking us to reverse engineering a transfer function from a board plot. Solve and see. Maybe, but it's really just detective work for engineers. Take a good look at plot magnitude plots shown here. We are plotting gains in decibels (dB) versus angular frequency omega in radian per seconds. Let's break it down step by steps. From 1 to 10 radians per second, the gain is flat at 20 dB, no slope here. That means no pulse or zero affecting the system in the range. At 10 radians per second, the gain starts increasing at positive 20 dB per decade. That's a clear sign of a zero. Then at 1000 radians per second, the plots start falling at negative 20 dB per decade. What caused a drop? Yep, a pole. So we have a constant gain that's called a k, a zero at omega is equal to 10 radians per second, and a pole at L, omega is equal to 1000 radians per second. So step 1, find the DC gain k. So we find out on the block plot 20 dB at low frequency. Remember that 20 dB means our magnitude is k such that 20 log k is equal to 20 dB. Now we use the reverse of log. Okay, get it? K is equal to 10. Now step 2, spot the zero. Upward slope of positive 20 dB per decade means 1 0 kicking in, and the corner is right at the omega is equal to 10. In standard form, that's 1 plus j omega per 10. Every time omega is 10, that terms double the magnitude slope. Now we see a negative 20 dB per decade drop at omega is equal to 100. That's one pole in mass speed. 1 per 1 plus j omega per 100. It times the gains, shaving off 20 dB each decade beyond 100. Step 4. Locate the second pole. And yet, we have got two poles in total. The second joins the party at omega is equal to 1000. So we get a 1 per 1 plus j omega per 1000. Double trouble for our high frequency gain.
All right then, with me, we go to the last step to obtaining the transfer function, which is uh, here we have the standard form. Before this, Andrew declared the standard form from the box plot given in question G. So here I want to share how to convert the standard form to the transfer function. The standard form, we have three standard form and one gain, which is 10. And three standard form is 1 plus j omega over 10, 1 plus j omega over 100, and 1 plus j omega over 1000. So the first thing is we need to factor out constant and express the equation in term of j omega to prepare it for simplification. Next, we multiply both the numerator and denominator by values that help us to eliminate the nested fraction like this. We have 10 over 10. So we eliminate the 10 under the j omega, so we will get the 10 plus j omega. We use identities. This is called identities like 100, 1 over 100 is equal to 10 over 10 power of negative 2, which make calculation easier, especially when combining the terms. So step by step, we reduce the equation until we get a single simplified form. Like at the last at the last part calculation, last answer, which is 100,000 and 10 plus j omega multiplied by 100 and 100 plus j omega, 1000 plus j omega. So it's the final transfer function we get after we do the calculation to simplify it. So it's give us to so it's give us the final transfer function that we know the gain we obtain is 100,000 and 1 the zero item, which is 10 plus omega, and 2 posts, which is 100 plus omega and 1000 plus omega. So this is the final answer we need to do when the question asks to obtain transfer function. Here we know that not only end with standard form, but we need to convert it to the transfer function, which is like this, which is the last answer we get lah. So that's all from me for obtaining the transfer function. So in the last part, we conclude that in two questions that we have answered, which is question B and question G. In question B, we know how to draw, how to build a graph box plot with the given transfer function. And next is we know how to obtain the transfer function with the given box plot in the question. So for the overall, that's in frequencies in this chapter, frequencies response of a circuit. We have no the frequency response of a circuit shows how the circuit amplifies or attenuates signal of different frequencies and how it shifts their phase. Plotting the box plot from a transfer function help visualize how a system responds to different frequencies in terms of gain and phase shift. Obtaining the transfer function from a box plot allows you to mathematically model a system frequencies response based on magnitude and phasor behavior. So I think that's all from our groups. Thank you for watching.